Hello, in this video we're going to talk about a variety of things that sit in chapter 1 of this textbook, where the textbook author is throwing all kinds of things together that they assume you know, but want to make sure. And so this is probably review from many of you, and if it's not, no problem, now's the time to learn. And so we'll start with the metric system. This was developed by scientists in France, so it's known as Système International des Unités. My French is not that good, but this is why we call it the SI system, or SI units. And so we have our set of basic SI units that you're probably familiar with, and then from those we can derive a number of other units. In chemistry we use volume quite frequently, and volume in liters is equal to a decimeter cubed of volume, and we'll see that on the next slide. Another example is newtons, which is named after Sir Isaac Newton, and is the SI unit for force and weight. And a newton is the amount of force you have to apply to accelerate 1 kilogram of mass, which is 2.2 pounds, at a rate of 1 meter per second squared. Okay, that's a little arbitrary, but it makes a bunch of sense because it's defined in terms of other SI units in a logical manner. So that's how derived SI units are put together. Generally, they make a bunch of sense. Okay, so let me talk more about volume in that, we use liter a lot in chemistry, and a liter is defined as the volume inside a cube that is 10 centimeters, or 1 decimeter, which we'll get into that in a second, 1 decimeter on a side. Now, if you were to take a cube that was a meter on each side, that's a cubic meter on the top of this slide, and that's 1,000 liters. Now, if you were to take on the bottom of the slide a cube that's 1 centimeter on a side, that's a milliliter. And so often that's why you hear, give me 2 cc's of morphine, stat! It's because a cubic centimeter is a milliliter. So they're saying, give me 2 milliliters of morphine, stat. Whatever they say in these hospital shows. And then one of the other hallmarks of the metric system is that you can jump orders of magnitude. That's a fancy way of saying if you had 1,000 of something, you could say you have a kilo something. So this works with any base unit. So you can have a kilometer, which is 1,000 meters, and we call it a kilometer. You can have 1 millimeter, which is 1/1000th of a meter. And those are the tiny tick marks on the metric side of your rulers, and so on and so forth. And we can do this with liters. We talk about milliliters and microliters a lot in chemistry, and etc. So the units here on the slide are the ones that we commonly use in chemistry. This is kind of the range over which we need to talk about. One other interesting thing about people is that they like to talk about numbers between 1 and 1,000, so we'll often change prefixes to put numbers into this range. So for example, I need to pipette 0.01 milliliter. Well, you're going to say I need to pipette 10 microliters because that's a lot easier to say. Other ideas, remember that density is mass over volume. I saw this written on a whiteboard once, and I'm never going to forget it, that we all love density. So here's the big heart that we love density. Why we love density, I don't know. And then if you put a line through the middle, you have an M on top and a V on the bottom. So density is mass over volume. Maybe that helps you remember it. Failing that, it's cute. Another thing to keep in mind is that mass and weight are different concepts, although on Earth they're numerically the same, generally. So mass is how much stuff there is, and then weight is how much force it exerts when it's pulled down by gravity. And conveniently the numbers are the same on Earth because we developed the system and made it that way. So they're not technically interchangeable, but the weight on the scale is the mass when you weigh something out. Then we also need to think about temperature. We use Celsius a lot in chemistry. We also use Kelvin, and they're interconverted by adding or subtracting 273.15. You cannot go lower than 0 Kelvin. And you can convert from Fahrenheit or to Fahrenheit if you need to. Generally, we just try to keep it all in Celsius when we're doing science. And the last thing is that it's incredibly important to include the units with your number. You don't say, I walked 5 today. 5 what? 5 miles? 5 feet? 5 steps? Right? These things are really important. You have to make sure that you always put the unit with your number, even if you think people might know, because sometimes they might not. Okay, another thing we want to talk about in our first chapter of fun is intensive versus extensive properties. It's not that complicated an idea, it's just one you might not have thought about before, so it's something we need to talk about and think about. So intensive means that it is independent of how much stuff you have. So things like density. The density of water is the same if you have a gallon of it, if you have a liter of it, if you have a milliliter of it, the density is still the same, and so we call that an intensive property. The same is true for temperature, viscosity, and concentration. The concentration one is really important because we use that a lot in science and chemistry, where if you have a big thing that's 1 mole per liter of concentration, we call that 1 molar. Well, if you have if you take a little bit of that out, it's still the same 1 molar concentration. And then you can do some math to figure out how much stuff is actually in there, but overall the concentration's the same no matter how much you have. That said, the mass is different, right? If you have more stuff, you have a bigger mass, you have a bigger volume. If you have more stuff, you'll have more thermal energy associated with it having a temperature and having some molecular motion. Of course, if you throw a sledgehammer versus a ping pong ball at the same speed, that's dramatically different amounts of momentum, things like that. So again, something you need to know. I'll ask you about it on a test. Just take the time to think about it. Okay, we also should talk about energy. It's really important in chemistry because reactions happen because they release energy, or there's other reasons also, but energy is a really common one that we need to think about. Or reactions may absorb energy, and we'll use things on purpose in order to get this effect, right? So we need to think about energy a lot. Energy is in units of joules, or the joule is the unit of energy named for a person, and 1 joule is 1 Newton times a meter, and so it's the amount of energy you have to supply in order to apply a Newton of force through a distance of a meter. So it's how much oomph you have to put in to accelerate this 1 kilogram object at 1 meter per second squared acceleration over a meter. And again, it has a nice definition, and there are times when we need to take this definition of the joule and break it into its constituent units that make up a joule. So you'll see on the info sheet for the exam that 1 joule equals 1 kilogram dot meter squared dot seconds to the -2. You'll see that on your info sheet because you might need it. Okay, and then broader, energy is the capacity to do work, and there's a lot of different ways that we can think about energy. And I'll let you pause it and read the slide. I don't need to waste your time reading it for you, but there's lots of different forms of energy, and they can all, in principle, be converted from one form to another, which I'll talk about on the next slide. So pause it, take a read, unpause it, we'll move on. Okay, again, all forms of energy can be converted from one form to another, and we think about this in the law of conservation of energy, in that the total quantity of energy is constant. So if your LED puts out light, well, that energy that is the light had to come from somewhere. And it probably came from a chemical potential energy, a chemical energy in the battery that then was transmitted as electrical energy through the wires to the LED. Something like that. Now, the textbook we use in our course has calculations of energy and power, and I don't see a reason to make you do those, so I skip them in my class. However, if you're not in my class, then you should ask your instructor and figure out what they want. Okay, last thing to talk about is percent error and accuracy and precision. So in common life, accurate, precise, we often will use these terms interchangeably, but they're not interchangeable. So accuracy is how right you are, how close a result is to the actual value, what it should be. And precision is how often you can get the same answer. If you did it 10 times, would you get the same answer? So in the picture here, the dots are individual measurements. There's 4 different scenarios here on the x-axis. And the answer is supposed to be 1 because you're measuring the density of water, which is pretty close to 1. So pause the video, look at these different scenarios and think, are they accurate? Are they precise? Are they both? Are they neither? So go ahead and pause it. Okay, so number one, since all the dots are really close to each other, it's precise, because the more times they do the measurement, the same answer they get. And then it's accurate because all the dots are right around 1. They're measuring 1 gram per mil over and over again. That's great. All right. Number two, it's accurate because if you take the average of those dots, it's pretty close to 1. It's not precise, though. These numbers vary all over the place. And then the third one, well, they're precise because all the dots are close to each other, but they're not accurate because the answer's wrong. And then number 4, that's a mess. You take the average, your answer's way wrong. You look at the precision, well, the numbers are all over the place. That's a do-over, we call it in the biz. Okay, so we need ways to represent accuracy and precision, to think about them, and to kind of convey this information to other people. And so the straightforward way to discuss accuracy is percent error. Oh, I'm correct within 3%, something like that. And so you calculate this by taking the difference between your measurement and the true measurement, so how far off are you, and then you scale it by dividing by the true value. Okay, now to talk about precision, we can calculate precision by repeating the measurement multiple times and then calculating something called a standard deviation from those different measurements. And we'll define this and do this in lab. We don't do it in the lecture course. But what we do in the lecture course is significant figures, and you do it in the lab also. This can kind of indicate precision, right? If you say, I walked 2 miles, okay, it might have been 2.5 for all you know, right? Like pretty close. Whereas if you say, oh, I walked 2.137 miles, well, wow, you really know how far you walked, right? And so the extra numbers there that I said, the extra significant figures, kind of imply precision. I mean, maybe I'm full of hot air and, I don't know, not actually precise, but it does kind of imply a level of precision, and which is why we are so big on significant figures in this class, because it really does matter. Okay, that's all I have for this video. Thanks for paying attention, and I'll catch you later.